For the kinetics extension topic, I picked something that isn't on the WJEC specs, but should be. And as a result, some teachers I know do discuss it, but probably not in the detail we're going to do it. It's the idea of integrated rate laws. And integrated rate laws are a way that is absolutely essential to understand in order to study the rates of reactions experimentally. But to get there involves some nasty maths, and so I think that's probably why the WJEC didn't want you all suffering through it. But it's an extension topic, so we'll suffer through it. First of all, before we get to the maths though, let's just think about a nice general first order reaction. A, our reactant, goes to stuff. We don't care about what the products are, we just care about the fact we got A. Well, if it's a first order reaction, we can immediately write the rate law is rate is K times the concentration of A. And now let's do something that I've alluded to, and indeed there are the occasional questions on it. Think about the units of K. K changes its units as often as my son changes his fancy beautiful t-shirts. Okay, essentially the order of the reaction determines the units of K. So let's have a look at that in terms of our first order reaction. Units of rate, moles per litre per time. Okay, concentration per time, change in concentration over change in time. On the right-hand side of the equation, we got K, which we don't know the units for, times the concentration of A. Well, concentration is moles per litre. So you can see you've got moles per litre on the left-hand side, moles per litre on the right-hand side. Those will cancel out. And that tells us that the units of K has to be 1 over time. It could be 1 over seconds, 1 over S, 1 over minutes, 1 over hours. Could see it written sex to the -1, s to the -1, min to the -1, hours to the -1, and so on. But any time that you see a rate constant that just has the units of reciprocal time, then you know that it is a first order reaction. Now let's get into the integrated rate law. And if you haven't done integration, don't stress it. Just kind of shut your eyes for a little bit. Don't freak out. And as soon as I need you to open them, I will say something. Okay. Right now, we're going from our first order, rate is K times the concentration of A. Well, rate, of course, is the change in concentration over the change in time. And because A is a reactant, this is minus. So this is just the fancy symbolic way of writing rate equals K times A. Now let's think about changing the concentration and changing the time in teeny little bits, which means that we're now not talking about deltas, we're talking about D's. So minus dA over dt equals K times the concentration of A. Let's rearrange that a little bit and stick a nasty, horrible integral sign in there. So what I've done is I've kept my dA on this side. I brought down A onto the bottom on the left-hand side. I brought dt up to the top on the right-hand side. I brought the minus sign over here, just for grins and giggles, and I've stuck some little integral signs in there. Now, the integral of 1 over something is the natural log of that something. And the integral of a constant is just the constant times whatever you're integrating, in this case t. So this becomes natural log of a, because that's 1 over a integrated. This becomes minus kt, because that's what you're integrating, k with respect to t. And then we're doing an indefinite integral, so we're just going to have plus a constant. Now, if t is 0, let us say that the concentration of A is just A sub 0. So the initial concentration of a reactant, A sub 0, and A is the concentration of the reactant as time goes along. So anyway, T is 0. That means this whole thing's 0. Concentration of A is A0, so this is log of concentration of A. So C is simply log of the concentration of A. So we'll put that in and rearrange it a little bit. So we put in log concentration of A, take the minus kt over to the other side, bring the log of A over to the C, the log of A0 side, and we get this first order integrated rate law. Very important result. Everybody who shut their eyes, open them again. This is very, very important. What it's saying is that when we're doing a first order reaction, we start with our initial concentration A0. We've got a rate constant K, and after time t, the concentration of A is this. in the light blue. So it's an expression that tells us about how the concentration of a reactant is changing with respect to time, because of course K is a constant, rate constant, and when you start a reaction, we've only got one starting concentration. And it was a little pulse. So I said that the big thing with our first order reaction integrated rate laws was the ability to graph things. So let's just graph a first order reaction, shall we? Let's plot concentration of A on the vertical, time on the horizontal. You've seen this plot before at the very start of the kinetics movies. Well, as the reaction happens, this is what goes on. The concentration of the reactant decreases sharply at first and then smoothing off. And of course, the initial concentration, A0, is the concentration at time 0, the concentration with which we start. Well, look at what we got here. We're plotting concentration of A against time. As time varies, concentration of A varies. And our integrated rate law shows us that. There's A0, the starting point. There's K, the rate constant. Here's the concentration of A, that's our vertical axis. Here's T, our horizontal axis. So this lovely little equation here is actually the equation of the line relating concentration against time. Now, of course, anytime you've got a curve, experimentally, it's lovely and it's pretty, and we think it's absolutely super and wonderful and beautiful, but we can't read too much out of it. But let's look at our equation here. Log of A0 minus log of A equals KT. Let me rearrange it a bit so it emphasizes more appropriately what this graph is. There's A, well, there's A all by itself, right? Log of it. Here's minus KT, well, that's the time. And of course, the minus is because we're going down there. And then log of A0 is the starting point. Okay, so you can maybe see with this way we've written it, how this is a little bit closer to this graph. But it's still pretty ugly. But think about your standard straight line graph. Anytime you've got two variables, y and x, and if they're related such that y is just some constant times x plus another constant, you get a straight line. Let's draw out x against y. There's our straight line, intercept of b, slope is equal to m. Well, now have a look at how I've written this here. First of all, y is one variable. Well, a is one of our variables. Well, I know if I plot a against t, I get this. But if I was to plot log of a against t, it matches up to a straight line. There's log of a, which is my y. There's t, which is my x. This is a constant, log of a0. And this k, crappy constant as it might be, is still a constant. So in other words, if I plot a against t, I get the curve, the equation of which is log of a is minus kt times plus log of a0. But if instead I plot log of a against t, well, now I'm going to get a straight line. And that straight line will have an intercept of log of a0, and it will have a slope of minus k. Well, of course, k is always a positive number, so minus k will be a negative number. So for a first order reaction, if we plot log of a against the time, you'll get a straight line. The intercept is the log of a0. That's not a whole lot good because you always know what you start with. But what's really, really, really cool is here is this slope, the value of which is minus k. Anytime you can take your data and plot a straight line out of it, it's nice, it's lovely. You'll get much, much more accurate, more precise data if you can fit a straight line to it. Plotting log of a against t for a first order reaction allows us to get a straight line, slope of minus k. Now that's all well and good, and certainly the questions that are in the quizzes that are associated with this will talk about first order reactions in which you have one reactant doing its stuff. But it's much, much more likely that reactions are going to have two components, A plus B, going to the products. Okay, and even in a nice simplistic situation, rate equals K times concentration A times concentration of B, A might be first order and B might be first order, but you have to worry about A and B if you're going to study this reaction. Well, a lot of times what you'll do is you will study reactions under so-called pseudo first order conditions. What that means is that you take a huge excess of one of your reactants. In this case, I'll pick B. Tons and tons and tons and tons more B than A. So that means, of course, going back to early concepts, A is very much the limiting reactant. More importantly, because you've got so much more B than A, you can assume the concentration of B hardly changes, and so B is constant. Okay, and the concentration of B at any time during the reaction is the same as the starting concentration. I mean, what I mean when I say huge excess, 100-fold excess, for example, so that if you're using up all of A, you'll only use up 1% of B. Well, in that case, you can have a pretty good idea that B is going to be a constant. Now, what that means is that we can assume that the change in A is the rate of reaction, so minus change in A over change in time. It's going to be K prime times the concentration of A. So that's up here, rate equals Ka times B, where K prime is just the original K times the concentration of B, which we just said is going to be a constant. Okay, so then you just do all the usual old thingies. Okay, and so now when you plot it, you'll still plot log of A against T. You'll still get a straight line where the slope is minus K times the concentration of B0. So as long as you know your starting concentration of B, which you always do, you can get the slope, you can get the value of K associated with this reaction, even though it's not a first order reaction overall, because it's first order in one reactant, huge excess of the other reactant, and you can still study the reaction effectively. So there we are, first order reactions studied via the integrated rate law, which is this extremely important relationship.